In this example, we're being told that y equals f of x is a solution to this differential equation right here, e raised to the x to the third. And then they provide us this additional information about it that says the initial condition f of 0 equals 4, which means when we plug in 0 to the original equation, notice they're talking about f there. So when I plug 0 into the original equation, the answer to all of that math should equal 4. And then in the lovely way that the AP Calc people like to do it, they say, which of the following is true? Which kind of means, guess what? You got to do basically 5 problems really fast to kind of see if any of them fit what you're looking for. So the first thing to understand about this is when something is a solution to the differential equation, it is the original function. And so what we know is whatever our original function is, f of x, that when we take the derivative of this, it needs to equal our differential equation, that our f prime of x needs to equal e raised to the x to the third. And so here you're really going to be tested on how quick you can get some derivatives done. So if I look at a right now, if I went to take the derivative of this, I'd work at it, break it up by pluses and minuses. The derivative of 3 is a constant, that goes away. And then as I take the derivative of e to the x to the third, this is going to be a chain rule problem. And my little saying that I use when I'm doing a chain rule, remember, you got to have different little recipes for all your different rules. My chain rule recipe goes d in times d out. The derivative of whatever's inside the function times the derivative of the out. So the in on this, the derivative of x cubed would be 3x squared. And then the out here, the derivative of e to the x, that just stays the exact same. And so now when I look and go compare that to what I know my derivative is, that is definitely not my derivative, so A is off the table right now as an option. When I go to do B, you can kind of quick on B. You should say to yourself, these are two things being multiplied. That's a product rule. And so a product rule is going to end up in an FG prime plus GF prime. Well, that's going to have a big old mess of stuff with a plus in the middle, right? There's no negatives in there, so it's not like any of that stuff's going to cancel out. So the odds of it being this equation at the end are slim to none. So I would probably, again, in the interest of time, skip on over that one. So I skip over B. I don't think B is going to be the right answer. Then I come down here and I look at my C option. And as I come to take the derivative of this, the derivative of 4, that's a constant, that's going to go away. But then how do I handle this piece right here? Well, that came from what they refer to as the Fundamental Theorem of Calculus Part 1. So the Fundamental Theorem of Calculus Part 1 says if I have a number raised to the x of some f of t dt, if I take the derivative of this, if I ddx this thing, then guess what? Derivatives and antiderivatives are inverses of each other. They cancel each other out. And what I'm left with is that original function just with an x plugged in there, right? So that equals f of x. So using that concept, when I come to take the derivative of the second part on C here, all I'm really going to get out is exactly what's inside here, except with an x plugged in. So then my answer to that would be e raised to the x to the third. So C is on the table as an option still right now because that matches up with my derivative. Going on to D, again, the derivative of 4, you would say, okay, the derivative of 4 is a constant. It's going to go away. And then as I come to do this next piece, again, it's any number can be on the bottom here. So this is, again, going to be that Fundamental Theorem of Calculus Part 1. So that's going to end up also giving me a derivative of e to the x to the third because I'm just going to take that x and shove it in there. And then as I come down to the last one, same idea here, right? I'm going to end up getting out f prime of x equals, and this is just what I've been doing except it doesn't have a constant in the front. So I raise that and I toss that in there. So this is e to the x to the third. So right now, C, D, and E all fit my derivative. They all have this derivative that I'm looking for here. Now's when I need to come back through and I got to work with this idea that when I plug 0 into this equation, I need to get out 4. So remember, function notation works the same even if you've got funky equations going on in it. So if I have f of x equals 4 plus 0 to the x of e to the t to the third dt, and I come through and say, what is f of 0? Well, all I do, function notation says whatever I replace x with here, you replace x within the equation. So I get out of this 4 plus the integral from 0, and then I plug in 0 up here, and out of there e to t to the third dt. Well, when we have bounds that match, this is one of those rules they want us to remember. When my lower and my upper bound are the same, no matter what that antiderivative is inside there, the answer to a problem like that is always 0. And so what I'm really looking at is now f of 0 is going to equal 4 plus 0. So f of 0 equals 4. So that is fitting my initial condition right now. So C has done everything that I need it to do. And so I could feel very confident right now at choosing C as my answer. If you needed to go on to these other ones, what you're going to notice is your integrals aren't going to work out. When I look at option D here, I get 4 to the x and then e to the t to the third dt. Well, when I do f of 0 on this one, plugging in for 0 there, I'm going to get 4, and then this is going to be 4 to the 0 e to the t to the third dt. You may not know what this antiderivative is, but you know that it's not going to end up equaling 0 because e is always above the x-axis, right? So whenever you're graphing an e to the x function, an e to the x function is always above the x-axis, so no matter what, it's always going to have some positive area. And that's what an integral is always doing. It's the area between the curve and the x-axis. So this would be 4, and then I'd be adding to it, or I'd have to switch a bounds here, or subtracting from it a number, and as soon as I change it from being a 4, it no longer matches this original function of what my initial condition needed to be. And then looking at e, it's kind of the same idea, right? F of x equals the antiderivative of 3 to the x of e t to the third dt. Well, if I do f of 0 and replace x with 0, again, I'm looking at an e function, which I know has to be above the x-axis. So this is either going to be a positive number or a negative number because I got to reverse the bounds on it. But either way, it's not going to end up equaling a nice easy 4 out of there. So that doesn't equal 4 either. So option C is going to be our answer. This again is another one of those questions that separates people from getting a 3 from getting a 4 and a 5. This one used differential equation knowledge and it used the Fundamental Theorem of Calculus Part 1. Thanks for watching my video. If you liked it, please click that like button and subscribe. And also share it with your friends and anyone else you know who might be crying about an upcoming AP Calc test. You can find more videos from me, more sample AP Calc questions, and my complete AP Calc study guide over at my website, apcalcprep.com. Have a great one.